Okay, so let's say you have a problem where you have to solve for x and y that are part of two triangles that you know are similar. So the first thing you'd want to do is probably find out the enlargement factor between the two triangles. And we do have a reference, which is the side of 5 and the side of 15. This is because these two sides are corresponding, and since we know that the triangles are similar, they're going to have the same enlargement and minimizing value as the other values. So to start, we'd probably want to do 15 over 5, which is equal to 3. And this would be the enlargement factor when you're going from the small triangle to the big triangle. So when you're going from small to big, your enlargement factor is going to be greater than 1. This is because if you have a value that's larger than 1, it means that the value when going to small to big is going to get larger. On the other hand, if you're going from big to small, the enlargement value is going to be less than 1. This is because, let's say you had 15 and you wanted to find what this side was if you didn't know what it was, and you multiplied it by 3. Well, that obviously wouldn't be correct because we know that this side has to be smaller than this one. So that we know that our enlargement value when going from small to big is 3. So this one would be for there. And then contrastingly, if you had 5 over 15, which is equal to 1/3, that would be the enlargement factor for going from big to small. So now that we have our two enlargement factors, we can figure out what x and y are. So let's say we wanted to solve for y first. So we know that 4 times 3, since we're going from small to big, is going to have to be equal to y. And 4 times 3 is 12, so we know that y is equal to 12. Now if we're solving for x, we're going from big to small, so we're going to have to use our big to small enlargement factor. So it would be 21 times 1/3 is equal to x, and 21 times 1/3 is the same as 21 over 3. So, and 21 over 3 is 7. So 7 is equal to x. Now, there's also another way you can do this. You can use proportions to solve for your x and y values. So I'll use that as an example too, but just because if you like proportions more, it doesn't mean that you can't learn enlargement factors, because more than likely they will be on an exam and they're really helpful for the future. So let's take x. Let's solve for x. So we'll take our initial value that we already know is correct, so 15 over 5, and to set up our proportion, we're going to need 21 over x. So the reason you have 21 on the top and not on the bottom is because the two values on the top are going to have to be from the same triangle. Similarly, on the bottom, these two values are going to also have to be from the same triangle. So this means that in our case, the top two values are both from the larger triangle and the bottom two are both from the smaller triangle. So you can solve this proportion however you want, but either way you do it, you're going to get some form of 21 times 5 over 15. And that, in turn, is 7, because we're solving for x, and we can check that value because we know how to do it with a proportion as well. So we know that 7 is equal to x. Now you can do the same thing for y, using the same proportion, just using the different numbers. And so that's how you would solve for x and y, using proportions instead of using an enlargement factor. So there's a lot of ways that you can solve problems like this, but the one way that will probably be the most helpful for the future would be the enlargement factor. But I know that when I was in integrated 2, proportions were way easier for me, so don't feel obligated to use an enlargement factor, but you will probably get a question on the test that says, okay, what is the enlargement factor going from small to big or big to small? And then you will need to know how to solve for this kind of stuff. So this basically right here covers enlargement factors and finding missing sides of two similar triangles.